All right, kids, we're going to start our study of integrals, which is the third hot topic in calculus. When I asked you in the very beginning of the year to research what is calculus and what's it good for, you came up with the fact, most of you came up with the fact that there's three parts to calculus. First part is limits, second part is derivatives, and the third part is integrals. So we are transitioning now from talking derivatives to talking about integrals. So that's Unit 6. Is exactly that. The look at integrals. So the region between area under a curve. Section 6.1 is talking about accumulation of change. But the region between a function and the x-axis is called the area under the curve. Under, in this instance, does not mean below. It means between the x-axis and the function. So you've got three pictures here. And if you look at where the area is between the curve and the x-axis, that would be, I'm going to highlight, you might want a highlighter. We get to color today. All right, it would be all of this. Right? The area, in this case it is, under the curve. But really they're talking about between the x-axis and the curve. And the second picture is a little different, right? If I look at the area between the x-axis and the curve, now my area is down here. And then if I look at something like the sine graph, this last thing, part of it's above and part of it's below. So you've got this little piece that's below, and then it switches, and now the area between the x-axis and the curve is up here. And then you go below. And so it can be a combination of the two as well. You're always, though, looking for what the area is between the x-axis and the function. So we're gonna highlight that too. There you go. So important things to remember. Now, let's take a rate of change function and examine its graph. The area under the curve gives us the accumulation of change, how much change is going on. So this accumulation idea is going to be important to us today too. You're on a road trip and you have a car on cruise control for 4 hours. You travel at 60 miles per hour. How far have you traveled? And so you have a graph here. You're 60 miles an hour. It never changes. Oh my goodness, I hope you didn't need a potty break. Over 4 hours. So I'm only looking at this up to the 4-hour mark right here for the first 4 hours. And so I know, just thinking about this, just think logically, right? Back to my original information, that if I go 60 miles per hour, 60 miles per hour for 4 hours, right? How far have I gone? Well, your hours cancel out. This was miles. And so I've gone 60 times 4. I've gone 240 miles per hour, right? Well, let's look at it graphically. Same idea. I have 60 miles per hour for 4 hours. And if I look at this, it's actually looking at the area of a rectangle. See how this is like a rectangular shape? I'm looking at how big is this area in here. How large is that area? The area of a rectangle, just like back in geometry actually, the area of a rectangle is the length times the width. In our case, we have 60 miles per hour. Watch your units there. Miles on top, hours on the bottom. And I'm multiplying that by the width, which is 4 hours. And lo and behold, hours cancel, and you've got your same answer, 240 miles per hour. So you can look at it logically, or you can look at it graphically and come up with the area between the function and the x-axis. That's an accumulation function. So the area, units for the area under the curve, you notice that the hours in our case canceled each other out. So the dependent unit multiplied by the independent unit, in other words, the unit for y times the unit for x. Those are the two blanks in that bubble. You'll see, like, this may be kind of confusing the way that it's written. Let's take some examples and you'll see it in action, and I think it'll make a whole lot more sense. All right, so we need to go back to geometry. I hope you like geometry because this is a lot of geometry today. We need to think about formulas for area of several different types of shapes. So like the first one that I'm going to talk about is the area of a circle. What's the equation for the area of a circle? And that would be pi r squared. What's the area of a triangle? A triangle, we might see triangles in the midst of this. That's 1/2 the base times the height. What's the area of a square? It would be whatever the side is squared, side times side, length times width, but because it's a square, they're both the same. We just talked area of a rectangle. That's length times width. And the other one that comes up is the area of a trapezoid. You might not remember that one so much. That one's 1/2 the height times base 1 plus base 2. I think that they may be the only shapes that come into play in what we're going to look at, but we'll add to our list if we need to. And so here's our next problem, number 2. The graph below represents the rate at which water is leaking out of a tank. The units are given in the graph. So we've got gallons per minute, we've got minutes. The other thing to take note of is the scale. This is a 1, this is worth 1, and this is worth 1. If I go back to this one up above, do you see how the scale is? This was a length of 1, but a height of 20. So make sure that you're in line with the scale. You want it to be, in order to do what we're going to do, you want it to be a 1x1 type box like this one is. So I'm looking at this. The units are given in the graph. How much water has leaked out of the tank after 9 minutes? Well, 9 is here, so I'm looking at the entire graph. And what I want to know is, what is this? Remember, an accumulation, how much water has leaked out is all of this area under the curve. Just like it was up above in that car problem. Okay, so there it is, area under the curve. Well, in order to calculate this, at this point, I have no function. They've given me no algebraic function, so I totally have to go by what the graph's doing. And what I'm going to do is I'm going to break the graph up, and you can choose any way you want to break the graph up into geometric shapes. So some of you might want to break it here. Oh, I see a square. I can figure out the area of that square. Some of you, with the way that I did it to do less steps, was I went all this way and I called this rectangle that I just created area 1. A1 I'm going to put. My first area. And then my second area is half of a circle. This is going to be my A2, second area. Because I'm thinking I've got to change my geometry. I've got to change my equation, right? I can't use the same equation for the rectangular part versus the circular part. I've got to use the right shape stuff. And then I'm left with area 3, and that's going to be a triangle. So break it up. You can break it up any way you want. The less shapes, the less work. So that's really kind of where it's at. So area 1, we're going to start with area 1. Well, area 1, I know, is a rectangle length times width. And so if it's a rectangle length times width, the length of my rectangle is 6, the width of my rectangle is 2, and I get 12. We'll talk units at the end. Go to area 2. Area 2, ooh, it's a circle, but is it a whole circle? And you say, nope, it's half a circle. So half of pi r squared is my formula. And so I'm going to take a half of pi. The radius is 2. All right, so that's going to give me 2 squared is 4. Half of 4 is 2. That gives me 2 pi. Then I'm going for area 3, and that's a triangle. 1/2 the base times the height. So 1/2 the base is 3, and the height is 2. Well, 2 times 3 is 6, half of 6 is 3. And then if I want to know how much water has actually leaked out of this tank in those 9 minutes, all I need to do is add up my areas. So I have 12 plus 2 pi plus 3, and I get an answer of 15 plus 2 pi. Now let's think my units. If it's gallons per minute, and just like I did up here, if it's gallons per minute times minutes, what happens with the minutes? They're knocked out and you're left with just gallons. Now, the problem, actually the units should also make sense, because how much water has leaked out? So many gallons. That would be, it wouldn't make sense for you to have an answer in minutes. That wouldn't be logical. So it has to the units have to line up with what the situation is. So that's how much water would be leaking out in those 9 minutes. All right, one more that shows something a little bit different before we do a couple practice problems. Number 3, particle is moving along the x-axis at a rate modeled by r of t, this function that you see. One is centimeters per second, and the other side is seconds. And so, here's what you need to know with this one. How far is the particle from starting position after 10 seconds? And so you're going to be able to figure that out based off of the areas and such. The deal is, though, for this one, that there's a couple things you have to think about. First thing is that, and this is over in your margin, and this is really super duper important, that the area below the x-axis must be subtracted. It's considered a negative area. All right, kind of like, so I'm going to bubble that around. That's important, super duper important. Okay, second thing that's super duper important is that you have to watch the scale. So I'm going to make a note of that too. Watch the scale. Because see how every box is not a 1-by-1 box this time? That your y's are going by 5s? And so that's going to be important as we work our way through this one. Okay. So, let's see how we're going to divide this up. I want to figure out what the area is between the function and the x-axis. So I've got a first little section there, I've got a section here, and then I have another section that's over here to go to 10 seconds. Sometimes they'll make it only go to like 6, so you got to watch what the problem's asking you for. This one wants you to go all the way to 10. So that's fine, that's no issue. Okay, so if I look at this, the first figure that I see is a triangle. So I'm going to call this A1. It's going to be my first area, A1. Kind of can't see the one, can you? The second one, I have choices. I can divide it up into a triangle and a rectangle and another triangle. That's what they did on the curriculum video. But do you see another shape that maybe I could use in the midst there that might make my life a little bit easier? Hopefully you're seeing that it's a trapezoid, right? So I'm going to take the area of this whole thing, so I don't have to split it into 3 things. I'm going to make it all just one and make it a trapezoid. And then this will be my A3. All right, so let's figure this out. I've got A1 is a triangle. 1/2 the base times the height, 1/2 of 2 times 10, right? The 10, don't forget that y is scaled differently. So 2 times 10. means that I have an area that equals 10. All right, the 2's cancel out. If I go to area 2, I'm going to come over here. Area 2 is a trapezoid. 1/2. Now the height of the trapezoid is kind of like its width. So 1, 2, 3. Times base 1. The bases are the parallel parts. So base 1 would be 1, 2, 3, 4, 5, 6. And base 2 is 2. Oh, wait a minute. 3. The 3 is representative. See, they got me. They almost got me. It's not 3. It does have a height of 3 boxes, but 3 boxes are worth 15. Oop. Good catch, good catch. All right, so I'm going to work this out. The 2's cancel. So it's really 15 times 6. And that is, I don't know. I'm going to go to my calculator. When I did this, I broke it up into the 2 triangles and the rectangle when I did it on my, for me. So 15 times 6 is 90. Okay, so this equals 90. And then A3, down here, is back to my triangle, and actually, isn't it going to be the same thing as the first one was? 1/2 of 2, and then the height is 10. And so the question is asking then, how far is the particle from the starting position to the from the starting position to 10 seconds. And so you would have to take your, I'm looking at this because the answer is different. That's my pause. They have -60 for that, or they have 60 for this. Let me go back to my trapezoid and make sure that the math here is right. So if I have 2, 1, 2, oh, this was a plus. That's what it is. Did y'all catch this? I'm so glad you're here. I wish you were here, then you would have caught it for me. 6 plus 2, not 6 times 2. Now let's see where that puts me. I can't cancel out the 2's, so let me go back to my calculator. Where's my calculator? Here it is. Let's try that again. So I have in my calculator, I want to know what half of 15.5 times 15 times 8 is. There we go. There's the 60 that I wanted. Okay. So making this correct, this is 60. So I'm going to take my areas and add them up, and that's the answer to part A. So sorry for that little delay there. 10. This 60, though, is below the x-axis, and we said anything below has to be subtracted. So be careful of that. So it's going to be 10 minus 60, and then this 10 for this last triangle is above the x-axis. So that's a plus 10, and I end up with an answer of -40. Now that would be -40. My units, centimeters per second, seconds cancel. This is centimeters. And what does it mean for particles moving along the x-axis if you're a negative? Are they going to be right or are they going to be left of the starting place? And the answer is negative is left. So this guy is 40 centimeters to the left. There you go. And then it says, all right, well, how far is the particle from its position at t equals 2 after t equals 8 seconds. So now they only want me to look at the portion of the graph that goes between 2 and 8 seconds. And so we did the math for that. That's this whole section in here, 2 to 8. That was this whole part here, area 2, that we know is 60. So that is 60 centimeters. And how far is the particle from position? It's 60 centimeters. They didn't ask me right or left. I guess they didn't ask me this one either. But because it wasn't, you could put the negative with this if you want. You could also say it's 60 centimeters left, if you want. Okay, so 2 problems I want to do from the practice. First one's number 2, same page. The graph below shows the velocity of a particle moving along the x-axis measured in meters per minute. At t equals 0 minutes, the particle is at the origin. All right, so I'm going to divide this thing up into geometric shapes so that I can calculate out where this thing's at in different times and such. So I kind of don't even look at the questions so much until after I've figured out all the areas, because they're all going to come into play. This one wants to know where it's after 2 minutes. This one's after 6 minutes. This one's after 10 minutes. So I might as well just go ahead and find all the areas and be done with it. So area number 1, let me do my highlighter here again. Right, here's one area between the x-axis and the curve would be this crazy looking area in here. And then the last one is this little itty bitty triangle at the end. Okay, let's figure out how we can divide this. Now this little piece first little piece is a trapezoid. So this is going to be area 1, a trapezoid. And again, you can divide this any way that your eyes see it. I'm going to take this one and make this area 2, that little triangle that's there. I know I have a half a circle that I have to deal with. So maybe this will be area 3. I have a triangle here that makes this area 4. That makes this area 5. And this little guy over here is area 6. Holy moly, there's probably an easier way to do that. Okay, so as I go through this, let's go through. Area 1 is a trapezoid. 1/2, a height of 1, and base 1 plus base 2. Base 1 is 1. Base 2 is 2. 1, 2. So this gives me 3/2. If I go for area 2. Area 2 is a triangle. 1/2 the base of 2, and a height of 2 is 2. Area 3 is half of a circle, half of pi. My radius is 2 squared. 4, half of 4 is 2. This is a 2 pi. By the way, you might want to note that, remember that this is negative, right? This triangle A2. A3 is also a negative, as will be A4, my rectangle. A4 is the base times the height. 1, 2, 3, 4 times 2. That gives me 8. That's going to be negative as well because it's below the x-axis. And then I have a triangle A5. Let's see if I can fit it all on my little sheet here. A5 is a triangle 1/2 the base of 1 and a height of 2. The 2's cancel, and that is 1. And then I've got my last one. This one's also a negative, right? A6, area 6, 1/2, a base of 1 and a height of 1 is 1/2. And he's back to being positive. Shoo! All right, so let's go and answer their questions. We have all the information now to be able to put it all together. Where's the particle after 2 minutes? Well, from 0 to 2 is area 1. Area 1 is 3/2. 1.5. Now units wise, meters per minute, minutes. The minutes cancel out and I've got meters. Where's the particle after 6 minutes? Ooh, 6 minutes. Now I got to kind of figure this out a little bit differently, right? Because now at 6 minutes, now my breakaway is here. So let me see if I can. And it's not symmetric, unfortunately. When I first did this problem, that's kind of why I chose this one. It's not like you can just take half of all of this negative area, because see how this leg over here has a different value than this leg over here. It's not symmetric where you can just divide it in half. When I did the problem, I divided it in half and I was wrong. So if any of you are thinking that, you got to rethink. Okay, so here's what we're going to do. Some of it we can use. Where's the particle after 6 minutes? Well, I know that I have the 3/2, the 1.5. Let's go decimaling. 1.5, that's for A1. I know I have A2. A2 is below the x-axis, and I've got all of A2, that's 2, right from here. Then I've got to take my square here. This square is 2 by 2. Also negative. Squares would be side times side. And then I also have a negative, so this, I kind of divided it up. I'm not giving it an A value, but so this little, where the 5 is a 2 by 2 square. That's what this is. And then if I look at this piece here, that is 1/4 of the circle, or that one is actually, because circles are symmetric, half of your 2 pi. So let's look at it that way. If I do half of 2 pi, that's going to get me where I am to 6. So let's see what that comes out to be. If I have that, I've got 15, I'm sorry, 1.5 minus 2 minus 4 minus pi. And so if I combine like terms, I've got -6, and I'm adding a positive 1.5. That gives me a -4.5 minus pi. All right, that's it. Sometimes the book said this. I don't know if you like this or not. They factored out the -1, and they said 4.5 plus pi meters left. We should put our meters with this too. And then where's the particle after 10 minutes? Well, that's adding all of these up. So if I take all of my values and add them up, I have a 1.5 that's positive. I have a -2, a -2 pi. I have a -8, a -1, and a +1/2. 0.5, since I'm doing decimals. And so I'm going to take and I'm going to add all of those pieces up. That's going to give me a -9, because you've got this 1.5 plus 0.5 is 2. 2 minus 2 cancel each other out. And I'm left with -9 minus 2 pi. And again, it's in meters. You could change it as you did this one up here, make it 4.5 plus pi meters left. But this is perfectly fine. So there's number 2. Last one, number 7. 7. Because this one's a little bit different as well. So number 7, the flow of water, all this thing about water, right? The flow of water in gallons per hour through a garden hose on a hot summer day is given by the graph shown above. Of the following, which best approximates the total number of gallons of water that passed through the garden hose that day? So if I'm looking at the area under the curve, then I'm looking at, I'm going to highlight it. That area and this area. Okay. So in this particular case, I don't have geometric shapes, right? I don't have a perfect square or rectangle or trapezoid, which makes this one entirely different than the ones that you had seen previously. So what you're going to do is you're going to take and estimate it by counting boxes. You're going to count the boxes, and then you're going to multiply that by, I should have written this a little differently, count boxes, multiply by the box value. And you're like, what the heck are you talking about? So if I look at one box, one perfect box, right? This guy right here. What is that one box worth? So I know the area of a rectangle, length times width. So it's 3 times 50. Well, 3 times 50 is 150. So each box is worth 150. And so what you're going to do is you're going to estimate the boxes. So you're going to count them. So if I look at complete boxes, this is a complete box. This is a complete box. Skip over the other ones for now. This is a complete box. This is a complete box. So you have 4 complete boxes. But then you also have these boxes here. And really, because this is symmetric, you could just figure it out what it is for one side and multiply it by 2. That might be an easier approach. Or you can just add up the estimations for all the boxes. But let's stay on this side, on the left-hand side of this thing. About how much of the box do you think this is? If the whole box is worth 100, this one you're going to estimate, and I said it was about 100. My estimation was 100. Now you could be somewhere in the hood. You could be a little different than that. That's okay. This box here, this one that's also just a part of the box, I estimated that to be about 50. It's like a third of the box in my, like when I looked at it. And then this box here is almost a complete box. So it only has that little piece that's missing. I said he was 140. And so what I did was I took these 2 full boxes, 150, here I'll put it over here, 150 plus the other box that's a full box, 150, plus my estimations, 140, 50, and 100. And I added them all up and I got 590. And then this side, because it's symmetric, I times it by 2. And so that gave me an answer that was 1180, which isn't exactly any of these, but you can see very clearly that it's close to that 1200 mark. The reason why we're off is because we estimated what these boxes were worth. So it should be, and they were nice enough to us that they gave us values that were pretty far off from one another, so you could tell which one was really the one you wanted. And that, my friends, is Accumulation of Change, section 6.1. Shoot me an email if you've got any issues or questions.